Welcome back to this channel. This video we are going to discuss about the summary of week 5 and 6 and which is equivalent to the chapter 2 atomic structure. So in chapter 2 we learn about Bohr's postulate and then quantum numbers and followed by electronic configuration. Let's start with the first postulate. Electron moving circular around the nucleus with quantized energy. Based on this postulate, at the same time, we can introduce you one formula, which is E energy equal to negative RH Ribot constant 1 over n square. Next, we try to substitute the value of energy level into this formula, and you will notice that the following value is obtained. And then when we plot it according to the value scale, then you will notice as well, the value actually is getting closer and closer. So with this, we can draw a energy level diagram, which will be looks like this. Next, look at the second postulate, which states that electron at ground state may absorb the energy and excited to higher energy level, at where we also can know it as excited state. So actually, we are using the first formula that introduced. Okay, and then we find the change of the energy at where the the formula in the green box is derived. So I won't repeat the derivation as we already discussed in the tutorial. So just for your information again, the formula in the green box here can use to determine the energy change of an electron excited from lower energy level to higher energy level. Next one, the third postulate states that at excited state, electron is unstable and will fall to lower energy level in form of light with the specific frequency and wavelength. So from here again, we also can apply the second formula that introduced just now to determine the energy release when an electron drops. Okay, so next, for your information again, electron can drop to any energy level and they will form different series and will be in different electromagnetic region. So this is the series that you already memorized: Lyman, Balmer, Paschen, Blanket, and Pfan. At where you will know that the n final, if in Lyman series, means that the question let you know that the electron is dropped to n equal to 1 and so on. So for the electromagnetic region, or we also can known as spectrum region, which include the ultraviolet, visible, and also the infrared. Based on the third postulate, where we understand that when the electron drop, it will release energy in form of photon with the specific frequency and wavelength. So here there is another two formula. So we consider the delta E equal to h mu, which is represent the frequency. So the formula for the frequency is mu equal to c over lambda. So and then this is the consider the third formula that we need to know. Beside from this formula, we have another formula which is 1 over lambda Ribot constant, 1 over n1 square minus 1 over n2 square. So we'd like to highlight here this part n1 less than n2 always actually is included in this formula. So means that all together in basically we have 4 formula to remember in the 2.1 Bohr's postulate. So the light emitted actually will be passed through a slit and a glass prism, and then the light will disperse into a spectrum and will call light spectrum. So this is the example of the light spectrum. So the Bohr line here is considered the continuum limit, and then the gap, which is the biggest one, will be considered as the first line. Now let's proceed to 2.2 quantum number. So as always in the class, I told you that quantum number basically is represent the IC number of each electron. And in this quantum number, each electron will have 4 quantum number in the set of N, L, M, and S. So next, we want to continue, which is what is the meaning of N? N basically is the principal quantum number. During the class, I use the analogy as it is a block and represent the energy level or is the orbit. So the possible value for the N is N equal to 1, 2, 3, 4, and so on, which it is integer and must be greater than 0. Okay, next is the L, which represent the azimuthal quantum number. In the block, we consider it is in which floor, which we can say that it is sub-energy level. So later, you will try to understand what is the type of orbiter and also what is the shape of orbiter. Basically, the possible value for L is L equal to 0 to n minus 1. So in other words, to say the L value always smaller than the principal quantum number. If the L value equal to 0, the type of orbiter represent is S and the shape is sphere. And for the L equal to 1, is referred to p orbiter, the shape is dumbbell. And for L equal to 2, d orbiter, and the shape is cloverleaf. So basically, we just learn these 3 shapes in this level. But for the number and the symbol of the type of orbiter, so it can be up to g orbiter. Now let's look at the third quantum number, represent with the symbol M. Actually, is referred to magnetic quantum number and is considered the room in the block. So actually, it is represent the orientation of the orbiter, and the possible M value is negative L to positive L. So if L equal to 0, so the M also will equal to 0, and the shape of the orbiter is sphere orbiter, and if L equal to 1, then the possible M value is negative 1, 0, positive 1, and the shape is dumbbell, where you will notice that basically they will at different orientation. Okay, this is what we consider at different orientation. Later we will look at the bigger diagram or so that we can label and for the label the type of the orbiter. So if L equal to 2, so we have the possible value negative 2, negative 1, 0, positive 1, positive 2, and here we will have 5 orientation, but all here are considered cloverleaf. So the last quantum number is spin quantum number. In the analogy, we represent it with the bat, and basically it is represent the electron spin. Either it's clockwise or anti-clockwise, which represent with the number positive half and negative half. Okay, now let's come and learn how to name this orbiter. So when we look at the shape is dumbbell, so we understand this is p orbiter, but this dumbbell is on the z axis, so we label this one as pz. If you know the dumbbell is this p orbiter is referred to which energy level, then you can add the number in front the pz. So for the next one, because the dumbbell is on the y-axis, so this one we will label as py, and the last one on the x-axis, so we label this one as px. So next, now we look at the d orbiter. So for the first one here, you will notice that the cloverleaf is in between y and also the x-axis. So this one we will note it as dxy. While for this one also is the cloverleaf, but this time it is on the z and also x-axis. So we call it dxz. Okay, and the last one here is z and also y. So this one we will label as dyz. While for the next one, the dumbbell or the coordinate is on the x-axis and the y-axis. So that's why we label this as dx squared minus y squared, while the last one is on the z-axis. So we consider this one as dz squared. Okay, so now we continue with the last part of chapter 2, electronic configuration. So electrons are filled into orbital based on the following rules. The first one is the Aufbau principle. Basically, it let us know that the electron will fill into the lowest energy first. And then next, for the Pauli exclusion principle, no two electrons with similar 4 quantum number. And the last one is the Hans rule, which said that the electron must be filled singly and then with parallel spin before pair up. So now let's look at the example. The first electron always will be added to 1s orbital as it is the lowest energy, okay, or the orbital with the lowest energy. So that let's say the electron is filled with upwards, then the second electron we basically is follow the Pauli exclusion principle, at where this electron still will fill up into the 1s because it is still the lowest energy orbital, but they won't fill up in upwards but have to be way downwards due to the Pauli exclusion principle state that no two electrons with similar 4 quantum number. And the third electron won't fill up in 1s orbital, as we know each orbital maximum only can fit 2 electrons. So the third electron basically will fill up into the 2s orbital. Okay, the fourth electron still will fill up into the 2s orbital. Okay, after 2s orbital is full, so next we'll fill into 2p orbital. Okay, 2p have 3 orbitals. So the first electron, the fifth electron fill up here will be filled up upwards, and then the sixth electron will next to it. Why? Because the Hans rule let us know that the electron must fill singly, means that one by one, and with the parallel spin before pair up. So the seventh electron came, they also will fill into the next orbital, and the coming electron will fill up to 2p, as 2p has lower energy compared to 3s, and they haven't full with electron, so this time they will fill with downwards. In this case, it is follow Pauli exclusion principle. Okay, so I just use this simple to recall back what we already learned in the tutorial. Now let's recall how to write the electronic configuration for ions. As we know that there are two types of ion. First is N ion, which the electron is gained and will be added into the orbital, follow the Aufbau principle. Let's look at one example. Electronic configuration for chlorine is up to 3p5. While the electronic configuration for Cl-, which means need to gain 1 electron, so the electron will add to the 3p, so that become 3p6. So this is meaning that 3p still have vacant and the energy is lower than 4s. So that's why the added electron is adding into 3p subshell. So next we want to look at the cation. As we understand, cation is formed when the atom when the electron in the atom is removed. So when we want to remove the electron, make sure you remove the electron from the outermost shell, which means the principal quantum number is the largest value. Okay, now as usual, we have an example, titanium with the proton number 22. So the electronic configuration is 3p6, and then we fill up 4s2. After 4s2, we'll fill up to 3d2. So when I want to remove the electron, Ti2 plus, titanium 2 plus, means that 2 electrons will be removed. But these 2 electrons basically is removed from the outermost shell, which is n equal to 4. So end up the titanium 2 plus is n with 3d2. Okay, next we are going to look at the anomalous case when writing the electronic configuration. Basically, it occurs in these two elements, chromium and copper. Here we just mentioned two because we just learned the first row of transition method. So according to alpha principle, chromium have 24 proton while copper have 29 proton. So this argon, this Ar is represent argon. So we understand that argon with proton number 18. So 18 plus 2 plus 4 equal to 24. So 3d4 and 3d9, this orbital basically we will consider they as partially filled orbital. Okay, then in the notes we understand that 3d orbital and 4s orbital are closely, so cause the one of the 4s orbital one of the 4s electron is easy to jump to 3d, same to the copper. Once one of the electron jump to 3d for chromium and for copper, so we notice that 3d5 we will consider this one as half filled orbital, while for 3d10 we will consider as completely filled orbital. So as we understand that half filled and completely filled orbital have extra stability. Okay, so basically I think we are end for this summary.